Okay, 1211, this is the second installment of our makeup of Chapter 7, which I've done so poorly on. So here we go. We just talked about how an atom absorbs that energy that comes in the form of light. But atoms are also what give off light. They emit light. And so if we were to have, let's say, a lamp that was filled with just hydrogen, then we could send some electricity through it, and that might excite the atom up to a higher level so that the electron is initially way up here in something like n equals 5. That's the fifth orbital. And it may fall down, as we see here, to something like n equals 3. In doing that, it's going to give off a photon of light, which I've shown here as maybe some red light. All right? And you can see through the experiment that when we do hydrogen, we get something that looks like this, where we get mainly, for an emission spectra, a blank stuff with a few colors, because that's really all that's given off is just a few colors. All right, here's some examples of helium right here, of barium right here, and if it was a black body, then its radiation would give off all the colors, and we'd be giving off what's called the white light spectrum, and it would appear white to us if we just saw it, but here it is all separated out by a prism. A good example of all this is right here. We can see the connection between, this is an emission spectra, and here's the same absorption spectra for mercury, for Hg. If you take a careful look, everywhere there's a bright line, there's a corresponding dark line here. So this kind of shows that any absorption can be immediately followed by an emission, and of course they're going to be the same size because these lines here represent the energy of the transition. Okay, they do not represent the energy of the orbital itself. They represent the energy of the transmission between them, whether it be an emission or an absorption. So when we go from this point up to this point, that might be one of these lines. Well, now that we've seen that again, the Bohr atom is kind of tough to play with. We've got to draw all these circles, and they're just a pain in the neck to draw. So before Bohr had come up with his idea, a guy named Rydberg had looked at a bunch of experimental data from people, these spectra, and he had put together a map that looked more like this, which is called, this is the hydrogen energy transitions, but this is called an energy level diagram. In this case, energy increases as we go up. We're starting at a negative number, and going towards 0, way up here. This is 0 joules, and this is a negative number of joules. There's a reason for that, which you'll learn in physics. For now, let's just accept it. So the key thing to see here is that anytime we've shown, this is all for emission, as you can see, these are all giving off light. We can tell that because the arrows are going from high energy down to low energy. That would mean a photon would be given off as a result. All right. If we map this properly, we would map n equals 1 would go here, n equals 2 would go here, n equals 3 here, 4, and so on. All right, those aren't important for what we're trying to do here. The key thing is that we can look at this and we can learn a lot from just looking at this. For hydrogen, it just appears that there's a whole bunch of energy levels and they're so low, just a single energy level, and the electron in the hydrogen can go all over the place to any of these guys. And if we happen to be dealing with anything that falls to the n equals 2 level, notice it's falling to the n equals 2 level, that's what visible light is. If it's falling to n equals 3, it's infrared. And if it's falling to n equals 1, it's ultraviolet. As a matter of fact, I'd like you to know that. I think that's kind of an interesting thing, that visible wavelengths for hydrogen, visible wavelengths fall to n equals 2 from higher energy orbitals. Great. Just so you remember, we talked about this in class, but there is a way to get these energy levels and actually calculate this value. It's E sub n is equal to minus r over n squared. And r is called the Rydberg constant, after the guy who did this work and put it all together. So you can calculate the energy level for any one of these, and we'll be back for more in just a few minutes.